Hey guys, welcome to day 10, Implicit Differentiation, part 1. So, just to break down really what we're talking about and where this idea comes from, first we need to talk about the differences between the explicit, which is what we've actually been doing this entire time, versus what we're about to do right now, implicit. So what I'm going to use is a very straightforward example and how this works, but effectively explicit just means you have an equation where it's y equals something, or let me get rid of the quotation marks there, or f of x equals something. When you derive that, you say y prime or f prime equals whatever the result is. Implicit just means, hey, that y variable might actually be with some other stuff. So we can have something like this: x squared plus y squared equals 1. That's the equation of a circle. You can even just have something basic as x plus y equals 2. Something simple like that works. So let me just show you how we've been deriving things normally with explicit differentiation, and now how we might have to worry about it when we do implicit. So example explicit, we're going to use, let's just do a really simple, let's do y is equal to 3x, 3x squared plus, 2x, something like that. So when we derive this, we know, oh, it's just y prime equals, okay, let's use the power rule here. So 6x, and then that just becomes 2. Easy, right? What I'm going to do now is I'm just going to completely rearrange this so that the y and the x's are, say, on the same side. So all we would have to do is just something like this. Again, same exact equation as the one on the left that I just did, just reordered. This is where we need to use implicit differentiation because the y is not by itself. And so the way we would approach this is the exact same way we do before. Take the derivative of everything. Derivative of 0 is 0. Derivative of 3x squared is 6x. Derivative of 2x is plus 2. And then this is where things get a little interesting. What's the derivative of y? Derivative of y is just literally the derivative of y. So you may put just y prime, but here's where we're going to change up with the formatting a little bit. Recall, derivative of y is the same thing as derivative of y in terms of the x variable. And then what you would do is you get dy over dx by itself, or the y prime, or the f prime, whatever you want to call it, the derivative of y. Add it to both sides, you get dy over dx is equal to 6x plus 2. Notice we got the exact same thing as before. The reason why we want to do this, though, is when we get like the equation of a circle. Here is where it's a little tricky, because if we get y by itself, right, we're losing half of the circle. You only get the positive half, not the bottom half, unless you explicitly show that. And so that's when we use implicit differentiation, and then we'll show you guys what happens when you have, like, you need to differentiate y squared. What does that really become? So the long explanation is use something called chain rule, and I'm sure you're probably sick and tired of hearing that, but that is effectively what's going on. You could also use the shortcut that we provided for here, but let me just show you just why we use chain rule in the first place, just by doing this first example, okay? So kind of like the circle equation, obviously not the exact same thing, it's x to the 5th plus y to the 7th, but it's the same concept that's being applied here. So if we take the derivative of this entire equation here, we get 5x to the 4th, x is normal, right? Because we're taking the derivative of the y function in relation to the x variable. So what happens here is it's actually chain rule. If you notice here, the outside function, so outside function is going to be y to the 7th, whereas the inside function is just the y. So if you remember, chain rule is derivative of the outside. Okay, derivative of the outside is 7 something to the 6th power, but you put whatever's inside with the inside function, so it's y, and then you multiply it by the derivative of the inside function. Wait, what is the derivative of the inside function? What is derivative of y? Oh, dy over dx, or y prime, or f prime of x. In this case, we're going to use dy dx. And so you'll notice, basically, in a nutshell, if you really break it down, all you gotta do is take derivative of y, and then slap on a dy dx afterwards, because chain rule basically shows us that no matter what, the inside function is y, always. And then last but not least, take derivative of 9. Well, 9 is a constant, so we get 0. And all we gotta do now is reorder it so that dy of dx is by itself. So we end up with 7y to the 6th times dy dx equals negative 5x to the 4th. And then all we gotta do is just divide by the y by 6. So we get dy over dx is equal to negative 5x to the 4th over 7y to the 6th. And that's going to be the answer for how we implicitly derive this. Or if you want to change it, you would say y prime is equal to whatever was just up here. Again, terminology is something you got to get used to. We tend to use the dy dx because what happens is later on when we get to multivariables, or as in there's more than 1 or 2 variables we're solving for, you got to be careful about what we're deriving at that point. So that's why I bring specific saying the dy over dx. Okay, let's just go through, let's find a couple other examples here that might be a bit trickier to deal with. Let's go with, yeah, let's go with some of these guys here. Let's try 4 and 5, just because we're throwing in trig, why not? So to differentiate this, okay, so I notice instantly we've got product rule here and here, but we've also got chain rule inside of this, right? So it's going to be multi-layered here. So let's start off with the first bit here. Okay, so in order to do it, we know that the first term is here and the second term is here. We'll deal with chain rule in a little bit, but let's use product rule. So product rule requires, okay, we take derivative of the first term. Well, derivative of the first term, it's going to be the 3y squared, and then you slap that dy dx on top, times the second term, which we'll leave by itself, plus the first term times the derivative of the second term. So we got to do chain rule here. I'm going to still write this out. If you're comfortable not writing this out and just doing it in your head, all to you. But I'm just going to write this out. So we call A is going to be the outside function. We're going to call that the sine. We're going to say B is the inside function. That's x squared. That means A prime of x is going to be cosine, and B prime of x is going to be 2x. Okay, so now that we know that, to take derivative of the second term, remember this is our second term here, we're going to take derivative of the outside, which is cosine, in terms of the inside function, which is x squared, multiplied by the derivative of the inside, which we found out was 2x. Parentheses, parentheses. Okay, good. So last but not least, we have the derivative of this last term here. So that means we are left with 6y multiplied by dy dx. Okay, that was just the first layer of it. Now we got to worry about a couple extra things here. We notice that there is a dy dx here and a dy dx here. Okay, so let's try to figure out, okay, maybe we can get those on the same side, maybe factor out the terms. Let's clean some things up here. So if we clean things up just a smidge here, we get, let's put dy dx in front here, dy dx of 3y squared sine of x squared. We get plus, let's clean this one up as well. We're going to put the x and y together. We get 2xy cubed cosine of x squared equals, let's put dy dx in front, of 6y. Okay, so again, the goal is to get dy over dx by itself, and so what I'm going to try to do is get anything that has the dy dx multiplied to it to one side. So what I'm going to do is I'm going to take that first dy dx on the way left and subtract it to the right side. So we get 2xy cubed cosine x squared equals dy dx, first is 6y, minus dy dx over that ridiculousness on the second half here, 3y squared times the sine of x squared. Okay, almost done, almost done. Notice that both terms on the right side contain a dy dx, so you can factor that out, just like we've done in Algebra 2. So we get 2xy cubed cosine x squared equals, let's see, dy dx quantity 6y minus 3y squared sine of x squared. And so last thing to do is to get dy over dx by itself. So we are left with dy over dx. Divide both sides by that ridiculousness. So we get 2xy cubed cosine of x squared. And I'm going to do two things in one. Hopefully you've noticed at this point that you see that there's a y term here, so you could factor out a y. And the reason is, you'll see in a second, factor out a y, 6 minus 3y sine of x squared. And hopefully you see that even though it's a crazy division problem here, you can cancel out one of the y's here. So really, you're left with 2xy squared cosine of x squared divided by 6 minus 3y sine of x squared. Yep, even if I factor out the 3 at the bottom there, because 6 and 3 are divisible by 3, not going to really change much, so we are good to go. Yep, that's it. Okay, so breathe for a second. Again, the hardest part here is the fact that we have this new term. I don't know if new is the right word to say, but it's a different kind of way of thinking about it. Again, tackle it the same way you would if you were doing your typical like f of x equals, I don't know, like 3x, right? Something simple like that. The only difference is it's just y equals 3x squared. What's the derivative of y? It's just dy over dx, right? So the difference might be like, oh, maybe instead of it being like this, your equation is y over 3 equals x squared. Same exact equation, just written differently. And sometimes you have to tackle it that way. Okay. All right, let's take a look here. What else could we do? We should probably do one of these problems here. Let's see. Let's scroll around. I guess we could try this one. Let's try number 5. Why not? Let's do number 5. I can't tell if you're cheering if I'm doing this or if you're skipping past this section. Any, comment or any sort of email would be much appreciated. All right, so if we take a look here, same process. Let's scan what's going on. I see that we have an outside function containing the inside, so most likely chain rule. So let's write this down. Outside function is the cosine, which means the derivative is going to be the, in this case, negative sine of x. The inside function is going to be x times y. Derivative of the inside function, ooh, here we go, product rule. Okay, so derivative of the first term, which is just 1, times the second term, plus first term times the derivative of the second term, so dy dx. Let's just clean this up a little bit. We get y plus x dy over dx. Cool. Okay, that's not too bad. So going back to the beginning here, let's skip that down. It's going to be derivative of the outside term of the inside term times derivative of the inside term, which we just found was this. Okay, it's going to equal x. Luckily for us, we only have one dy dx, unlike the previous problem, so nothing too crazy to worry about here. So let's go ahead and get that dy dx by itself. I'm going to divide by the sign. I'm going to divide by this giant term first, so we get y plus x dy dx equals x over the negative on top, sine of xy. Okay, not going to look pretty, but we just roll from here. We're going to get x dy dx equals negative x over sine of xy minus y. And before we divide by the x, do I want to clean things up? No, because I'm going to notice that the x will cancel out the first term x there. So let's bring this over. If we divide by x, we get dy dx equals negative x over, recall when you're dividing x to both sides, like this x to both sides, it's basically doing this. And then that's going to change to that. So we can just stick the x down here, which you'll notice will cancel out with that. So we're left with negative 1 over sine of xy minus y over x. Again, answers don't need to look like the cleanest things ever. This is a disgusting looking answer. The point is, are we comfortable enough to be able to derive this even if the y is not by itself at the beginning? You can still differentiate it. It's going to be a bit trickier, but it is doable. That's the idea. Okay, let's try one of the problems down here. Might as well do the last one because why not? Okay. All right, so let's do a quick hot take here. So for the last one here, number 8, I'm just going to make sure that we talked about this because should be fine here. I'm going to do a quick pause for a hot second here. I was like, wait a second, I don't think we talked about this yet. Let's go and talk about this. And I was like, good thing we talked about this here. Okay, so it's going to ask you, okay, what the heck is a normal line? And you might think normal just means like, we talk about the tangent line, right? Not necessarily. So when we're graphing something, let's just do it, our classic x squared function. We know the tangent line to say this point right here would roughly look something like this. Slope of the tangent line at that point roughly looks like that, right? What's going to happen is when there's something called a normal line, let's do this in orange, or let's do, yeah, orange. When we talk about the normal line is basically from this point, when you find that tangent line, you want to find what is perpendicular. So it's going to look like this. Now, I wish I could say this for those of you taking physics, because maybe you would know physics at this point, if you would, or know this particular part about physics. But when we're talking about in physics, when there's an object, and let's just say that there's an idea of a force pushing in this particular direction, we would say the normal vector, or the normal force, would be pushing in that vector as well. So it's the idea of being perpendicular. So in that case, Same process as before, basically the same that we've done ever since the beginning of talking about tangents to, or the tangent line to that specific point. But first, let's break things down here. So what we got to do is we got to figure out, okay, so we've got our function here. We know exactly where the x value we want to be is at. So let's go ahead and find out the derivative here. So to find the derivative of this, we're going to take 2x minus, okay, here we go. So we've got 5, and then let's do the quantity of here in this case. So that means we're going to have, similar to what we just did with the cosine xy function, it's going to be derivative of x, which is 1 times y, plus x times derivative of y, which is dy dx. Cool. Should be good to go from there. Yeah, should be good. And then derivative of y over derivative of x equals 0. So let's just clean this up a little bit here. So let's go ahead and subtract 2x. And in this case, I'm going to distribute the 5 minus. Okay, we're getting there, we're getting there. Let's add the 5y here. Factor out dy dx. And we're left with our derivative, which is going to be okay, so we've got the derivative, which is the slope of the tangent line, right? So that's a start. We'll go from there. But the only issue is in our function here, or in our derivative function here, notice we need an x and y value. We're given the x value at the very beginning. How could we find the y value? And hopefully, we think back to algebra 1. We're given the original equation. Could you figure out what the y is if you know what the x value is? And yes, we can. So the way we're going to go about that, we're going to go up here. Let's move this out of the way, just to have some space. I'm going to move this over. If I plug in x equals -1, we get -1 squared plus, minus 5 times -1, y plus y equals 13. All right, let's clean this up. We get 1 plus 5y plus y equals 13. We get 6y equals 12, which means y is equal to 2. Okay, so now we know two things. We know x is -1, y is 2. So that means here, we can just go ahead and plug that in. We therefore know dy over dx is equal to -2 times -1 plus 5 times 2. Yep. And then -1 plus 1. So we're left with 2 plus 10 over 2, which then leads us to 12 over 2, which is 6. So we know the slope at that tangent line is 6. So to find the normal line, so slope of normal, recall when we do perpendicular lines, we take the reciprocal of the original slope and then slap a negative. Simply just like that. That's all it is. So at this point, we are good to go. Yeah, we've got an xy, we got the normal line slope. So what I'm going to do is I'm going to do the cheap, lazy way of doing about it. We're going to use slope-intercept form. So let's copy things that we know. We know that the y is 2. We know that the slope is -1, 6. We know the x is -1. Solve for b. So we get, well, that's disgusting. 12 over 6, 11 over 6. So finally, the equation is going to be y equals -1, 6x plus 11 over 6. There you go. Cool. You should be equipped enough at least to get through the practice sets. Should you have questions, definitely let me know. Again, terminology is the hardest part of the implicit, and once we get to part 2, we'll then do more of the advanced techniques there.